We are once again here with the CERIAS seminar held weekly. And this week, we have somebody that has been involved in cybersecurity for, well, really 30 years, a long time, been deeply involved in not only research, but in education, was one of the people involved with one of the very first centers of academic excellence, where he continues to be director. And this is at the, as you can see, the University of Idaho. So Jim Elvis Foss has just a long career. You can read some of his bio here. You can find him online. He's worked in a number of areas, including, as you see here, in source code analysis. He's worked in quantum. He's worked in, I think he did some work in IDS as well. And so he's got a lot of experience. He's going to share some of it with us today with some insights into function boundary detection in stripped binaries. And so please welcome Professor Jim Elvis Foss.
All right, thank you, Spaff. Yeah, and I've known Spaff at least 25 years, if not longer. So this has been really exciting to do this. I'll just jump right in. I got a lot to share with you. So the problem we're facing here is compilers translate source code into binary images, executable code. A stripped binary does not have a symbol table, doesn't have information to help the analyst figure out what portions of the code belong to which. So it's not obvious where a function starts, where functions end. And the problem exacerbated by if we use different compilers, different architectures, different compiler options like optimization options. The common ones people look at are O0, which is no optimization, O1, O2, O3, which do different levels of optimization. Even your programming language choice, so you're compiling C, C++, Fortran, some other language. And so to have a general purpose tool that can do this analysis is a tricky thing. If we can do this analysis, it will help us when we do reverse engineering, when we do decompilation, when we look at that executable and want to figure out what's going on. Can we do unit level testing of the binaries? Can we look at, hey, let's find a function and now analyze it for a vulnerability? Well, I have to know where the function is first before I do that. Can I do binary patching? So if you look at the DARPA Cyber Grand Challenge, if you're not familiar with it, I urge you to look at it. It was back 2014 through 16, was take a binary, analyze it, add security features to it without breaking functionality or performance, all automated. Well, to do that, you need to know where the function starts are. So an example of one, this is all using AT&T syntax from OBJ dump for the Intel compiler. This happens to be 32-bit Intel. Compilers do weird things. ICC compiler for optimization in 32-bit executables, normally data is pushed on the stack, passed on the stack. However, in 64-bit executables, the first several parameters are actually passed in registers. Intel, in their compiler, the ICC compiler, decided they liked internally within a function or within a program to pass the parameters in registers. But to be compatible with external functions that would call that, they would pass things on the stack. So the first two lines here, as things are passed on the stack, they copy them into registers. Then they fall through to a second part where they just use those registers. So internally within the program, it can call directly here, passing everything as registers. If an external program called it, the external program would pass things through stacks. So we have two different entry points for the same function. Which one's the function start? Symbol tables. ICC, actually, here's an example. They took one function, which I'll show a little later, broke it up into 5 constituent parts. Sometimes you'll have multiple symbols pointing to the exact same function. So we have to look at that. What happened here with the Intel compiler? They found a function that passed a parameter as a constant. The parameter was a radix. This was converting a string into an integer. So is it a 16-bit string? 16, base 16 format, base 2 format, base 4. So if at base 16, there was a switch statement at the beginning of the code that said, oh, if it's base 16, do this, base 2, do this. The compiler caught that, figured that out, and said, hey, let's create subfunctions, one for when it's base 16, one for its base 2, and only combine those together and optimize them together and pass everything as a constant and deal with it. So it compiled different code. And actually notice the code here is a little different because here it knew it was 16-bit, here it knew it was, or base 16, here it was base 2, so it did things differently. But it took a single expression, a single function, integer constant, and expression.c, and broke it up into 5 functions. So what's the function? Here's another example from source code. We have a while loop here that keeps repeating until there's an error, then it generates an error. Well, it'll generate code like this. No, there's a jump here in that while loop, and a bunch of no-ops. And then the actual beginning of the while loop. That's an optimization option to allow to fit on an address boundary. Well, so the jump's actually here, but certain tools like IDAPRO thinks, oh, this is the end of the function because there's a bunch of no-ops after it, because this looked like a typical pattern matching end of a function. And I've seen tools where they do training with machine learning. And they say, oh yeah, a bunch of no-ops, that's a pattern matching the end of the function. In this case, it's not. So we have to figure out how to fix that. Here's another example where we have a star RAX is a jump pointer. So this contains the address. You dereference the contents in this address and jump to that. Commonly used in switch statements. So you have switch case statements, case 1, case 2, case 3. Compilers generate a lookup table, calculate it, and use the jump pointer in that lookup table to figure out where to jump to. IDAPRO couldn't figure that out, so figured it must be the end of the function. So these are things that we have to look at and figure out, and there's a whole lot of other things. There's unreachable code, there's other things. So how do we do this? Well, what we did, and I know I'm talking fast, and you can slow me down if you have to. We did what we call a static semantics-based approach, and there's some other approaches that have been done. What we did is we used obj dump, not the best way to do this, but we started this as a tool and never, experimental tool never fixed it. So we took obj dump to generate actual source code like this in text, and then we parsed the text, fed it into what we call our GIL data structure. For GIMA is our tool. I should mention, so I did this work with Dr. Jia Song, her first name J-I-A, my first name Jim, J-I-M. So we merged those two together to get GIMA. So our GIMA intermediate language data structure is where we maintain everything when we do the disassembly. So we use obj dump to feed data into our GIL data structure. We also read the raw binary executable linking format file, the ELF file. We track in the disassembled code all the jumps, all the calls, all the returns to figure out, hey, these are addresses we know about. We figured out where code was and where data was in general sections. We found all instructions that explicitly referenced code and data addresses. We looked at the information about dynamic libraries. We determined if functions are actually aligned on specific byte boundaries, like every 16 bytes, every 4 bytes, or they're just randomly through, based on the ones where we have hard-coded addresses for, because we can see if I can go here, you often have the hard-coded addresses in a lot of code. And that's where we started. And then we said, well, there's exception handlers, and exception handlers list a block of code that they handle an exception on. So we'll grab that information, give us other analysis of where the code is. And we looked at also where the exception handlers are, because they're part of the function where they're handling the exception for, even though they're not directly reachable. Because if you did a control flow analysis of a program, you're not going to find the exception handling code that's at the bottom. So we looked for that. We looked for the jump pointers, and we did a pseudo symbolic execution where we took every jump pointer. I'll go back here like this one. We said, oh, it's RAX. Well, let's work backwards in the code to figure out where RAX is populated. Oh, it was populated from the context of RADX here. Well, RDX was populated from RAX. We work our way back to figure out if we can find out where in memory that jump pointer is, where that table is, calculate all those table addresses and say those are all part of the same function. This works about 90% of the time in what we have. Then we go through the code and say, okay, we've got this, let's start going. Start with something we know is the start of a function, start at a call, and work through it, analyzing all the places where an instruction is a target of a jump or a call or something, or instructions where the control flow leaves. We call these inflection points, places where the code diverges from our linear flow. So calls, jumps, returns, etc. Walk through all these inflections where we're leaving the code. So we're stepping through the code, beginning to end. Let's see, where's my... So we're going through the code, beginning to end. Every instruction is executed. When we get to a point where we say, oh, this could have been a jump or target out, that's something to look at. Then we find the next one where it was a jump out and we look at. And we decide when our analysis, is this part of the same function or is this leaving the function? That's ideally the goal. So we're doing a control flow analysis saying, are we in there or not? Now we got a lot of problems. Some code does what it calls tail jumps or tail optimization. If the very last instruction of a function is a call to another function, there's no need to return back to the original, because it's just going to return again. You have nested returns. Optimizing compilers throw that out. So at the end of the function, we may see a jump instead of a return, or a jump instead of a call. We have to be able to detect that. Sometimes we have a call to a function, but it's a terminal function. It's like exit or abort. So the code after that's never going to be executed. So should it be part of your function? So we went through and we did all this type of analysis and determination. Let's see what else. We can get to the next one. Come on. Okay. My slides are not changing. Here we go. And then we go through, say we're at the end of a function. Now we look at the next several block instructions and say, are they part of a function we already know about? Or are they not? If they're not, we put the start address of that next block into a table. We'll come back and look at it, and we move forward. So we go through, find all the targets of calls, calculate them as functions, find any code or instructions, opcodes we didn't know about, assembly instruction we didn't know about. We go back, analyze those. Every time we find a function that's a terminal function, we say, wait, I'm calling these non-returning functions. I call exit. Well, if all my program does is prints things out and then calls exit, my function is non-terminating. Or excuse me, terminal. So if I call a terminal function exit, and that's all I do, my calling function is terminal. So we go back and say, oh, who calls that? Because since it's a terminal function, anything after a call to that doesn't exist. So we reapply this. It's fun. It's a lot of code, and I'm going faster again. I apologize. We've done all this type of analysis. How do we do the terminal function calls? Well, we know certain system calls in the GCC standard library are terminal. So we hard code those in. And then everything else, like I said, if all execution paths of a function call one of these terminals, the calling function is marked as terminal. We throw that whole function that we analyzed back into the unknown space and reanalyze it to maybe see if we had combined too much. Because without doing this, we would sometimes combine multiple functions together into a single one, thinking it was a single one, because we didn't realize the control flow stopped. And then we clean this up. Sometimes at the end of a function, after a return or a call to a terminal, there's a jump over a bunch of no-ops. And all it is basically a no-op. So we clean that out. We clean out some padding. We look for other padding. We look for embedded data and mark it as embedded data. We do all this. We clean it up. We say, now we've got the functions. So quick that's kind of what we do. Now, how does it work? We're measuring this executable. We're going through this code and we're trying to say, oh, this is the start of a function. This is the end of the function. How well does it work? This is kind of what I kind of want to get to here, because I think this is the fun part. So we measure our true positives. If I said this byte or this instruction is a start of function, I'm right, it's a true positive. If I'm wrong, it's a false positive. If I completely missed a function, didn't say anything about it, it's a false negative. So for function starts, we wonder, did I get the right location? Is this truly the start of a function? And I have to deal with, what if the symbol table had aliases or other things? So we've dealt with that. And function boundaries, did I get the right length? Is this the last instruction? What if I'm short? Is that okay? One of the papers we looked at actually said, yes, that was okay. Why? Because some compilers, like the Intel compiler, counts the padding bytes between functions as part of the preceding function. Other compilers like GCC and Client do not. So they said, well, it was a hack on the student's report. They said, oh, well, because compilers do things differently, we'll just say if it's short, it's okay. I don't like that hack. What if the symbol table shows 0 length? Built-in functions don't have a specified length. So we've never matched the length. So we have to think all about that when we're doing our analysis. We have to think, what is the true ground truth? And from my point of view, if we are really good at this, as long as you had the function starts correct, everything after that function start to the next function start could be part of the same function, and you're good. Because all I really need to know is the start of the function and assume all the bytes afterwards until the next function start are part of the same. If you have code that is dealing with obfuscation, they try to mess up the binary and make it harder to reverse engineer. The code in a single function will not be contiguous and things will break. We're assuming we're not dealing with that problem. So prior work that people did in this area, and I'll explain this in a minute, used terms precision, recall, and the F1 value to measure how good we are. Precision basically says how correct are our answers. We reported a bunch of things to be function starts. True positives where we're right, false positives where we're wrong. So true positive, the percentage of things we reported, so true positive that are right. True positive divided by the sum of everything reported. High precision means you have a low false positive rate. Recall, how many of the functions did we actually even talk about? So our true positive divided by the sum of true positive and false negatives, which is the total number. This is the total number of functions n. High recall means you have a low false negative rate. And we want low false positive, low false negative. F1 is now a weighted average of precision and recall. So 2 times P times R divided by P plus R. Accuracy, and I'm going to come to this in a minute, is what a lot of people say, well, how accurate are you? Accuracy actually means something mathematically different than these. And I'll come to, like I said, I'll come to that in a minute. I'm also going to hint at this. I'm going to come to better. We're doing percentages. We're talking about, and a lot of the tools do this. They say, hey, I've tested 5,000 binaries. Here's I got 98% F1. That misses the big picture. And so I want to talk about that. So let's first, how accurate is accuracy? Let's talk about this. So we have something we call a confusion matrix. The columns specify reality. So is something positive or negative? So if I'm trying to detect something, a vulnerability, an attack in network traffic, a function boundary, true positive means that's really what that is. That's one of these. True negative means it's not one of these. So negatives here. Predictive positive is where I'm saying, yes, I think this is a function boundary. I think this is an attack. If I get it right, that's the true positive. If I get it wrong, it's a false positive. I said, this is a function boundary. I was wrong. Type 1 error. This is an attack. It's not. This is a vulnerability. It's not. You have COVID. If I'm right, true. If I'm wrong, and I said you had COVID, false. Predicted negative, I said no. And it could be, I said nothing. in most of our detection tools, you know, if I'm looking at network packets, I'll say, here's the ones I think are attacks. I'll ignore the others. Function boundary. I list every address I think is a function start. I don't say anything about the other ones. So it's assumed those are negatives. If I'm right, it's a true negative. If I'm wrong, I missed one, I missed a function boundary, it's false negative. Okay. So consider this. Let's assume there are rare instances of what we're looking for. Function boundaries, right? I've got, you know, 100,000 assembly instructions and 100 functions. Most of them are going to be not function starts. So maybe in this case, I have 10 things 1,000 things I'm looking at. So 1,000 instructions, 10 function starts, and 990 non-starts. So this is reality. All right. Let's assume my tool misses every single thing I'm looking for. It says there are no function boundaries. So I say everything's at 0. I've got the 10 real ones wrong. And I've got the 990 ones that weren't function boundaries correct. Accuracy is basically saying, how well did I do in this diagonal? Well, in this diagonal, I did pretty well. I got 990 out of 1,000. I was 99% accurate. My tool that did absolutely nothing right was 99% accurate and 100% useless, or 0% useful. And this is, I've seen on several papers, people talk about, oh, I'm accurate. Well, mathematically, accuracy means true positives plus true negatives divided by totals. And if you have a low prevalence of what you're searching for, accuracy is the wrong thing to report, and you should never have it in your papers. And I've seen it in some of these papers, function boundary, we buy 98% accuracy. Well, what's that mean? Let's look at another one. If this is precision, precision says how many of these are right, how many predicted positive right? Well, we predicted nothing positive, so we're 0. Recall says how many of the actual function boundaries did we find? We found 0 of them. So our F1, the weighted average is 0 and 0 is 0. So we're 99% accurate, but 0% precision recall in F1. Here's a different one. Let's say, hey, we split it up 3 different ways. We predicted some things. We found some things. We predict some things that were wrong, and we missed some. Precision, 5 out of the 10 reported is 50%. Recall, we found 5 out of the 10 real ones. That was 50%, so F1 is 50%. But I'm still 99% accurate. I got 990 out of 1,000 right. So what I don't want to see in these things is people reporting about the negatives. If the negatives overwhelm the data set, throw them out, analyze the other 3 parts. Those are the areas that are relevant. So when we look at this research and the data I'm going to be showing you, that's what I'm talking about, this relevant part. How much of these things I actually found, and how much, you know, what I said I found, how much of that was right. All right, so how do we do this? Sorry, that was my teacher aside there. Following models of prior work, we took bin utils, core utils, and find utils. There's 129 unique programs. We took spec CPU, oops, this wasn't updated, but there's basically 60 so much unique programs in each of these data sets. They include some Fortran code, include C and C++ with some exception handling. Some require position independent code, so that was interesting. We compiled everything with the GCC or G-Fortran compiler, Clang, and the Intel compiler. We compiled them using optimization options 0, 0, 1, 2, and 3. We also compiled the Chrome browser because it's big, just using the default. How do we know if we're right? We looked at the symbol table of an unstripped binary. So I should say we compiled these unstripped. We extracted out the symbol table, got all the right data. Then we stripped all the data and ran our tools on the stripped data. There are some hidden symbols in the text section that we had to look for, listed functions in text sections, removed all duplicates. We noticed some functions had multiple entries. For now, we count those as separate functions. Then we ran our results. So summarizing what we did with GEMA, using this, With GCC, we had an F1 value of 99.96. So basically, we looked at 1,512 files. They contained 1.66 million different functions across both 32 and 64-bit with all the optimization options. Out of the 1.66 million functions, we had no false negatives. We found every one, and we reported 150 incorrect. So 150 false positives. This actually happened in some of the spec CPU benchmarks where in testing, spec is for performance testing. They take standard tools and modify them to do the test. One thing they do is they jump out early out of functions or comment out code or jump out early. In spec 2006, they jumped out early before it did things like printouts and other stuff that they didn't want to actually do. So there was technically some unreachable code. Our tool actually detected and said, hey, that function never calls this, it must be part of another function. When actually it was just unreachable code the compiler, optimizer compiler didn't throw away. We also had some functions that were too long. In several of the compilations, there was extra code after the function actually terminated that we couldn't tell if it was just extraneous code, but we detected it. But again, 0.5%, so not too bad. With Clang, we did a little worse. And with ICC, Intel does such weird stuff. We did a little worse, but not too bad. Now, these are the averages over the 1,500 some odd files. Let's look at what other people did. So Tiffany Bao et al. Did a machine learning based approach. Shin et al. Did a neural network approach. Andressi et al. Did a graph theoretic approach with a tool called Nucleus. We compared ours to Nucleus. IdaPro, well-known tool for doing this. We did this actually, the versions I'm showing today, we didn't test with the free version, we did the commercial version. NSA's Ghidra is a free tool that does a lot of things IdaPro did. We tested with that. But what did we find? Well, if we look at things other people did, like Andressi or Bao, they report things this way. They say, oh, here's the different tools we looked at, IdaPro, BAP, Dynance, Nuclear. We looked at 32-bit or 64-bit different compilers, and we gave our numbers, precision/recall. Here, precision recall. So they gave their results using these raw numbers. And this is what you normally see in a paper. I don't like this. Yeah, I can do this too. And I can say, hey, here's the F1 values. You know, and 99.96 is better than 99.27. We win, right? 98.81 is better than all these 70s. We win. Okay, that one we do win on. But what does it really look like? You know, we're talking about the mean, the average. What does the mean mean? I use the same data set for all tools, and if my numbers are bigger and better than their numbers, I win, right? That's what I often see in a lot of these publications, and this is one thing I'm railing on just a little here. Because are you always better? If not, where and why? Right? Let's look at the average income in Idaho compared to the average income in New York City. Or maybe let's pick universities, average income at University of Idaho of faculty versus average income of faculty at Purdue. Purdue's going to have a higher number. But maybe we add as an adjunct to our university, Elon Musk. Now, when we look at the average, suddenly we win because one person drives all the data up. The average for all of us is much bigger than the average for Purdue because Elon Musk beats everybody. I want to see the results. So I say this when I'm talking to groups of students. You have to do better than just show me these numbers. You know, are there a few instances where I'm a lot better? Do these skew the means? So we actually did a scatter plot of the data. We dealt 3 columns of data, one for GCC, one for ICC, one for LLVM's Clang compiler. And we looked at IdaPro F1 for function starts and plotted that. And they have a number, right? There, let's go back to their number for GCC was 92.73. Or here, actually, look at this. ICC 72.14, Nucleus was close, Ghidra was close. But this is what the data looks like. And notice this from 0 to 100%, so they're all over the place. With GCC, the blue being a little higher. We look at Nucleus. Nucleus is struggling on ICC. in clusters of this. We'll come back to that in a minute, and doing pretty well in others, but again, some places they're having some issues. Ghidra. Now let's look at this versus this. Who's better? Or who's better here versus this one? The data's all over the place, and you can give me a raw number, but I don't know who's really winning. Now I know who's really winning. It's us, because this is our, oops, this wasn't zoomed in. Here's our zoomed in one. So this is from 0 to 100%. Our tool, all three, there is blue underneath the green, underneath the red. So yeah, we obviously win because we're not all scattered like this. If I even zoom it in from 70% up, I notice a few places we have problems. This was a decompilation error by OBJ dump. I don't remember what this one was. So some of these I can look at. We can also look at it a different way. I can say, how well did we do overall? So here, this is a histogram. I'm binning it. What percentage of binary were the tool's F1 values for function starts fits the x-axis? So how many of the F1 values are 0 to 9%, 10 to 19% up for each of the 1,500 binaries? This one actually is for a data set where we did 97,000 different binaries. It's one I'm still working on. So 80% of our stuff is up in this 100% range for GEMA, where IDA Pro has 10% of their stuff in the 100% range. Ghidra and Nucleus have nothing in the 100% range, but they're in the 90 to 99% range. That's where they're doing pretty well. So if I zoom in on this a little, from 96 to 100%, again, we're up here at 100%. Then things where we're 99% F1 value, 98, 97. Ghidra does pretty well here and then drops down. Nucleus is a little slower. So it's another way of visualizing the data, looking at our results and say, hey, did we do well? Did we win? More results. Chrome. Default option, there's 353,000 functions in Chrome. It's a 90 megabyte file. We had 8 false negative function starts, 1 false positive function start, no false function ends. So we did pretty well on that one. Take this a little further. Again, average, we're talking average. Averages are just a single value. You can do better than that. I just showed you that. I want people to visualize the data, report in the graphs, the visualization in the report papers, visualization data. Again, we normally see these tables. I want to see charts. You know, here's histograms of the combined data sets, where things fit in, or the scatter plots. Now, here's one I want to talk about for a second, because this, when we were doing our research, was really interesting. So right away, we saw there's some problems with the spec benchmarks. The Unix benchmarks, we were good, except there was something weird here. So we decided, let's dig in. These are interesting. The places where we're not successful are interesting. So we looked at those. What we did is we grouped it by optimization level, 01, 02, 03, to see if there was something there. And sure enough, in the 01 optimization is where we're seeing some issues. That is interesting. And now notice this is 80 to 100%. I'm zooming in. So then I thought this was sorted by name, then by optimization level. Name's not useful. I actually, in Excel, when you plot these, you can click on this and it highlights and tells you, hey, this is the row that it is. You can look at that and find out which binary. I started noticing and looking at these. Some of these were smaller binaries. So we sorted by size and notice the loops here, especially this one. Well, what happens here is there's certain things we fail on. And if this one, if I'm failing on 20 functions out of 100, or, you know, out of 110, I'm down here in the 80 some odd percent F1 values. If I'm failing on 20 out of 10,000, I'm up here in the 90s, 99s. We looked at this data and found out all of this was from the Unix utilities data set. All of the utilities in that data set were using the same file that they were including. So even though we had 129 files compiled 16 different ways from Sunday, they actually had the same base code that was compiled the same way. And in the L1 optimization option, our tool was not recognizing that the function starts correctly for the way this was compiled. And the fact that certain of these tools were really small, it drove the data. So we found out what the error was, fixed this, and ran this to the top. But our numbers were still actually like 98%. We thought we were winning, we were doing well, until we visualized the data and realized we were winning some places and losing in others. So we did the analysis, we looked at it, we visualized it, we fixed it, and now we're at 99.8% F1 values instead of 98%. 98 still sounded good, but I like 99.9 or 8 better. So I encourage my students, encourage people, and when you're graphing this and showing them papers, to show this stuff. These are the interesting things. Okay, I went fast. So questions?
There's one there in the Q&A, Jim.
Yeah, so have we been using any coverage guided binary fuzzers? Not yet. We are looking at it. GEMA is in Python right now, so it can be run on any platform, but it's currently only working on Linux executables, 32 and 64-bit Linux. We are working on the, I've got a student right now working on the Intel things. Originally, GEMA was developed for the Cyber Grand Challenge, so it was on a specialized platform for just that. We ported it from that to the full 32 and 64-bit Intel. And it was all written in Java back then with some C, and we modified it, moved it all to Python. Probably a mistake. It is definitely slower in Python, but it was easier for a lot of the students to work with. Yeah. So how did O1 result in lower accuracy? Actually, what happened was just the way the optimizing compiler worked, it set things up in a pattern that our analysis tools did not recognize. And so we combined multiple, we were actually missing function boundaries. We were merging multiple functions together. We were missing a function end. How did we find it? One, figuring out which binary it was, going through the raw data, figuring out where the errors occurred, and then looking at it and staring at it for a while, and then like, huh. So one thing that we have here that's really interesting, like I said, we're still working on this to try and make it better. We have these data sets and just have to rerun things. So my current data set uses 97,000 binaries, but there are multiple compilations of a lot of the same code. And so an error in one thing may appear multiple times. The current data set we're using from a tool called BinKit, where they have like 6 versions of the client compiler, 6 versions of GCC, and they compile those using 6 different command line parameters. So compile the same executables into lots and lots of different variants. We're still having some problems with link time optimization as one of the options because it breaks, OBJ dumps decompilation fails on some of those. It's misclassifying things as instructions that aren't really instructions. And we're since relying on that, we can't fix that. So, but a lot of this has been just looking at it, thinking about it, visualizing it, playing with it, and keeping track of the old versions of code. Because too many times, like, oh, this is a problem, I'll fix it. I rerun it and said, yeah, it fixed it for that one case and broke 1,000 other cases. So our numbers actually went down. So it's been a lot of trial and error back and forth for everybody working on this to make sure that we're always making incremental improvements. A lot of graphing, a lot of spreadsheets of the data, a lot of version control. And it's been, we started this, like I said, the Java version of this probably back in 2014. Redid it into Python probably in 2018. It sat for a couple of years not being touched, and then this last year or two, we've been redigging into it again because we want to get it ready where we can port to actually not only Windows, but ARM architecture and some other architectures. So we're trying to modularize everything we were doing to make sure that we can pull out and say, this is an Intel specific module, replace it with an ARM module. What else?
Well, you got a comment thanking you for the talk and another question just posted.
Yeah. How does symbolic execution stack up against static analysis? Can it evaluate functions with 100% accuracy given it's not vulnerable to disassembly inaccuracies from optimizations? Okay. So symbolic execution, as you're going, how do you know you've entered a function? Right. So some functions, like I said, if the last instruction of your function is a call to another function, the optimizing compiler could turn it into a jump. You don't see the call, you don't know you're in the function. Second, in a lot of programs, is unreachable code. There are functions there that you'll never execute. And if you're not executing it with any type of execution, symbolic or otherwise, because maybe it's unreachable, it's still part of the binary. It still exists. It's still something that an attacker can use if they use any type of control flow attack. So the symbolic won't detect it. Also, we're faster than symbolic execution would ever do. I can analyze most binaries in seconds with this. Of course, I haven't been paying attention to the amount of time now because I got a nice machine I'm running on. So I have 60 processor cores, and I just run it all, 60 versions of this simultaneously on my set of 97,000 binaries. I go to lunch, I come back, get the results. I should say 60 processing cores and 2 terabytes of RAM, so I don't have to worry about swapping. What else? Any other questions?
So, yeah, you've gotten several very positive comments here. I wanted to ask you, you sort of alluded to this, but what are some further steps? Where are you going to, you had mentioned other architectures, porting into something other than Windows, maybe taking it out of Python, maybe including some machine learning in it. I mean, what are some directions where you're interested in taking this?
So one thing we're trying to do is beyond just the function boundaries, because we're pretty close to being done with that part. What else can we analyze? What other properties about a function would be useful for cybersecurity analysts? So we're detecting, is it from the raw binary, is it a variadic function, variable length arguments? Once we can determine that, then we can look, are there controls in place to prevent you from overrunning? So maybe I can look at, if it's a total standalone binary and not a library, can I look at the maximum number of parameters that were ever passed to that variadic function and make sure there's a control in place to make sure you don't overrun it? Maybe we can do some type analysis and say, hey, these are parameters or local variables that are pointers, and we're going to do some extra controls on those. Because eventually what we want to be able to do, we did this Cyber Grand Challenge, partially, we were able to use this, decompile the code, add stack canaries and some other features to the functions, recompile it and re-execute it. We want to be able to do better on that because it wasn't perfect when we did it with the Cyber Grand Challenge. We want to make it so we don't break the code, but we add these features. So those are some of the things we're looking at right now. Our main focus has been in embedded systems for some of the things we're doing. So it is analyzing it for something that's not a library, but a standalone piece, full function. But we do also want to look, what if we do this in a library? What if we do this when somebody's calling dynamic library? How do we deal with all that too?
Great.
One thing we want to be able to do with this function analysis too is, there was a question about fuzzing. We want to deal with fuzzing. Can it help me with fuzzing if I know more about what these functions are? I heard a dog.
that was at my end here. You have another question in the Q&A.
That was the same one. It was just a typo. Oh, no, that's different. Is there a way of decompiling malware from binaries? Well, depends how well it's hidden in the binary. If they're using any obfuscation techniques or stuff, we're not, I'm assuming decompilation as an input to what we're doing. So if the decompilation fails because of obfuscation techniques or other things, we're not going to do it. And there's lots of different obfuscation techniques out there in terms of just, changing the binaries or encrypting and have it self-decrypting as it's going. We're not dealing with any of that.
All right. Well, we'll leave it open here for another minute or two, see if other questions occur. I think this is a very interesting area to be able to do this. There's a lot of application, not only in code analysis, but in re-engineering code. So that's
one thing I'd like to, in the long term, look at is how do we protect the developers from themselves? You know, for years I have said, when you're dealing with security, you're dealing with the fact that bad guys lie, cheat, and steal. So when I was doing crypto protocol analysis, for example, people say, oh, just assume somebody's sending you the right message. I said, no, I'm going to assume they're sending me the wrong stuff because bad guys lie, cheat, and steal. Well, I've been adding for the last several years to that, bad guys lie, cheat, and steal, and good guys make mistakes. So how do we help the good guys and stop them from making mistakes when we're looking at the code? How do we help the developer who's downloaded a library from the internet and doesn't know if it's secure or not? Doesn't know this, what the security concerns, if it has vulnerabilities. Can we help them analyze that and fix that as they embed it into their tools? Because surprisingly, a lot of people download things from the internet and put it into their commercial tools.
Yeah,
it's a surprising thing. I started saying that our students nowadays program via Google.
Yeah, and Stack Overflow.
And Stack Overflow, yes, exactly. Nobody writes anything from scratch.
And well, it's the same thing as a fellow academic, right? We have problems with students trying to find ways to cheat, and it's always the case that they seem to copy from the people who have the wrong answers, so they're easy to find. The people who reuse code, who don't know enough to actually check it for boundary conditions and failures, that's a lot of our problem right there. Yeah, I could see a lot of interesting applications for this.
Yeah, I know somebody who has a software vulnerability analysis tool. What he does is he goes through Stack Overflow, finds commonly used code with vulnerabilities in it, and searches for instances of that in other people's work. The commercial code. He says, oh, I know somebody's going to download this and embed it in their commercial code. Says, I'm not going to look for new things. I'm going to look for existing things. So,
well, one of the things that I'll put to you before you get to this other question that's in here, I don't know if you've looked in detail at what SolarWinds, the hack and the SolarWinds did, where they introduced something into the compilation process as it was being recompiled and then took it out again, so that the binary and the source code didn't reflect each other at all. It might be interesting to think about how your work could be used to find those kinds of problems. Dick Clark, who gave the talk last week at our symposium, actually mentioned this as, I guess he kind of called it a grand challenge. I don't think he used those words, is to be able to find things that are introduced into the supply chain in a way that doesn't really alter the source code. So, I'll just leave that for you as a thought. And there's another question in the Q&A.
So, oops, I'm going to put in chat. I put it in the Q&A too, a link. So an earlier version of this work was in 2019 ACSAC. So there's a lot of citations and references from that date related to this area that are in that paper. I don't have a more recent version of this paper yet. There have been, if you do, some function boundary detection, there's been some more recent work that people have looked at. But I don't have links to those right away, so.
All right. Well, you've generated a lot of interesting questions and thoughts here. You've given us some references to look at for future work. I would encourage people to look. You can also do searches on Jim's name.
Currently, besides my wife having one paper, I'm the only Alsfoss out there with publications, so that makes it easier.
Yep.
My son is a PhD student now in English, so that's going to change, but we should be able to differentiate our publications at least.
Yeah, I would expect they wouldn't overlap by much. But you might set that as a goal for someday, is to do a joint paper. But in the meantime, thank you so much, Jim, for speaking. It's been too long since we've seen you, and continued good luck with what you're doing. I hope to see you in person before too long.
Yeah, I'm going to my first conference in a couple years. I'm going to NDSS the end of this month.
Oh, excellent, excellent.
So
Well, as life resumes, we'll see where it takes us all. For everybody who's listening in, please tune in next week. We'll have another seminar speaker, and until then, everybody have a good week.